Okay, hello everyone. Today's session, network layer protocols and IP addressing. We're focusing on layer number three. I think after the last session we did, I think we discussed the network models and we discussed protocols as well. Uh, 7 layers for the OSI model, 4 layers for the TCP IP. So when we're talking of the network layer, we're basically talking of layer number three. And as we discussed last time, its main responsibility was uh, routing, finding the best path to the destination. And this mainly makes use of IP addresses. So we'll get to look at exactly that in this session. I'll skip the forward objectives to describe the main protocols at the network layer, the concepts, classification of IP addresses, and special addresses, calculate IP networks and subnets, use the IP network addressing address planning methods. So basically here we discuss the main type of protocols that we have. We introduced IPs version 4, um, probably version 6 as well. Then we do a little bit of subnetting, and basically that will be it. Network layer protocols. This layer is often called the IP layer. Protocols include ICMP, IPX, in addition, IP. So common network layer protocols, I think it's a must. You have to know them. We definitely have IP, which is used for the addressing. I cannot write on this one. Okay, so we have IP, which is used for unique identification of every host on a network. We have ICMP, which is used for messaging, control messaging. That's a control messaging protocol. We have IP version 6. We have IPX. Those are some of the common network layer protocols that we have. And I think, as we said, with every layer, it's a must that you have to understand the type of protocols that belong to that layer. So for this one, all the routing protocols, I think we're going to be doing routing that belong to this layer, including obviously IP and ICMP. Starting with IP. IP is the name of the protocol file with small content, it defines and describes the format of IP packets frequently mentioned. IP refers to any content related directly to the internet protocol. Function, I think that's where we have importance here. It provides logical addresses for devices and at the network layer responsible for addressing, forwarding data packets. We have two versions, version 4 and version 6. So IP, I think this is the most important protocol at layer 3, mainly responsible for, like I said, identifying devices in a network. Also used when we are routing, trying to find the best path through the network to the destination. Versions, we have version 4, version 6. Version 4 uses 32 bits. Version 6 uses 128 bits. Um, we are slowly migrating to IPv 6 because of the number of IPv4 addresses is the pool is getting exhausted. Arupera basically. That's why we now have version 6. So we started with version 4, but because we no longer have addresses with respect to version 4, we are now moving to version 6. Right. Data encapsulation, I think we defined this in the last module. Why can I not write here? Okay, I need to write on the screen just a minute. Let me do this. Mm. Okay. You can write. Okay. Let me leave it at that. Okay, data encapsulation. I think if I need to write, I'll probably need to pull this up. Let's see. Just a minute. I think I didn't enable editing. Probably why. Hopefully I'm able to do that now. Right. Data encapsulation. So I was saying I think we defined this when we did the last module. You can't write. Which kind? Yeah. I cannot write the mess in it. Allow me to try to fix this. All right. I think we're good. Right. Data encapsulation, as we discussed in the last module, is basically addition of headers and trailer to our PDUs as we move down my layers Edu. Starting with the application layer, we discussed the PDU being data. And as we move down the layers, but not Shikapa transport layer, we add this information. So this is a header, a transport layer header. After adding, we get a segment. If a segment goes down, we add another header. It's now called a packet at layer 3, frame at layer 2. Then it's converted to bits for transmission at layer number 1. So data encapsulation is basically the method where we add extra information to our data, which contains the message we are trying to send. At this point, I think it's very important understanding what we call the PDUs, protocol data units, starting with data at the upper layers. Then we get the segment, packet, frame, bit. So every time I mention a segment, it should click that we are talking of information at layer number 4. And if you hear packet, it's information at layer 3, frame information at layer 2, etc., etc. Data will not just be data. A message will not just be a message. A message will be defined by which layer it is at any given moment. So data encapsulation method of a process of adding headers and trailers. Then we have obviously data de-encapsulation, which is a process of removing those headers and trailers. There we have a packet. That's the format we have for a packet. When you are saying format, we are basically trying to look at what is contained within the header and what is contained within the trailer as well. So if you're looking at this, we have Ethernet header. So this is layer number 2. This is layer number 3. This is layer number 4. This is our message. This is layer number 2. This is trailer. So this is the trailer of layer number 2. So when we are saying we're adding extra information, what information are we adding? Overally, we are adding a header, but at a header, it is a number of views that are in it. As you can see, header red panapa, it translates into version, header length, total length identification, various number of fields. But I think the most important ones you need to notice is the one against the source IP, a destination IP. So Patino added a header. Basically, what we are adding is we are adding the IP addresses. That's where we are adding where the information is coming from and where it's going, the source IP and the destination IP. We also have very important fields like the TTL, time to live. I think you need to understand what what the TTL field does. This is the protocol which which is the layer 4 protocol that is being used. We have the version which can be IP version 4, version 6. We have the checksum, which is used for error check. So we have a number of flags. Basically, every field you need to understand what it is responsible for. But I think the ones that I've highlighted, I think are the ones that are very important to understand at this point. The total length, this is the length of the whole header. We have header length. Not sure what's the difference between those two, but you definitely need to understand with every field header length, probably that's the length of the header. Not sure about the total length. So go through all the fields as you're going through your literature and understand with every field energy. Data packet fragmentation. This process of the process of dividing a packet into multiple fragments is called fragmentation. The sizes of IP packets forwarded to a network may be different. The size of a packet exceeds the maximum size. If it exceeds the maximum size, the packet needs to be divided into several smaller fragments before being transmitted. All right, when you're discussing fragmentation is basically breaking down our information to a suitable size so that we can then transmit. Size is very important when we are transmitting. If you have a message is not sent, it's just a huge chunk. Size is very important. You realize not every layer, but most of the layers, you realize the message size is being reduced. When we discuss the presentation layer, I think we discussed the issue to do with compression. It means message size is being reduced. When we discussed the transport layer, we talked of segmentation. That's another form of reducing the size of the message. When now we are discussing at layer 3, we have fragmentation. Is another form as well of trying to make the size of our information smaller. Why? Because transmission requires specific sizes, and information yedu can achieve from the upper layers. Yakakura. So we have specific sizes, defined sizes, depending on the layer 2 technologies we are using. Depending on the layer 2 technologies we are using, you are going to realize, for example, Ethernet size size frame yedu, when you're using Ethernet, size yedu is between 64 bytes and 1518 bytes. So information ikabva iri musoro and it's more than this size, it means packet will basically be dropped. If it is less as well, that packet will also, that frame will also be dropped. So size is very important during transmission. How size is managed, we have things like compression, segmentation, segmentation, and fragmentation. You just have to realize it's different layers. When you're talking segmentation, that is layer number 4. When we're talking fragmentation, that is layer number 3. But I think the end goal remains the same. Is so that you have size at layer 2, for example, being between 64 bytes and 1518 bytes, provided your layer 2 technology is Ethernet. So fragmentation, data fragmentation, dividing a packet into multiple fragments. Why? Size is very important for our transmission. Size is, I think, transmission it becomes a bit complicated. Right, time to live. We have a field that we identify from the IP header. So even though header ready, this field, TTL, it specifies the number of routers that a packet can pass through. Once a packet passes through a router, TTL is reduced by 1. So TTL is a mechanism which is used by our network to avoid a scenario where we have a packet just going through the network, never stopping. So if I have a scenario equity and the number routers like this one, so let's have another router here. So I have three routers here, 1, 2, 3. If I send a packet from this host A and the destination is not on this network, what happens? That packet is sent to the router. The router tries to find the destination network. It doesn't find it. It sends to another router. That router sends to another router. And the packet continues to circulate within the network trying to find the destination. Especially if you have what we call default routes. If you have default routes configured, packet rako rinoramba richingotendera network. Now imagine if we have a lot of packets like those, it means network yedu could probably come to a halt where we have a number of packets being processed and adds enough value to the network. So router redu processing power yayo is being taken by my packets asina kwaruenda. That's a problem. So to fix that problem, we have what we call the TTL. Every packet parinenge riri kusendwa rinoassignwa a value. Value iyoyo, it determines the number of routers packet roro, the number of hops it can have. So if, for example, TTL yedu iri 10, it means router device yedu painobva from a router iri kuenda apa inovha reducer kuita 9 ichienda pane imwe router 8 up until yaita 0. Ikaita 0, that packets get dropped because rinenge risina kwariri kuenda basically. And that is TTL for you, used basically to avoid a scenario where we have packets just roaming in the network as Arusha destination. Protocol field, I think they're going through every field here. The protocol field identifies the protocol that will continue the process, that will continue to process the packet. It identifies the protocol used by the data carried in the data packet so that the IP layer of the destination sends the data process mapped to the protocol field. Usually, understanding of this protocol, you can look at the layer 4 protocol that is being used. So as information is being encapsulated at layer 4, there is a protocol which is being used at layer 4 before information end up at layer 3. So the protocol field basically identifies the protocol that is being used in the upper layer, the layer 4. So these are the numbers. If it's TCP, if it's UDP, it's either 6 or it's 17. So you are realizing, I think, as we go to my fields, these are just numbers. Akawanda ash. If not all of them, they're just numbers. My numbers you are representing how packet track will be treated as it goes through the network. All right, that's the protocol field. And as you can see, they didn't go through all the fields. But like I said, I think you definitely need to go through all the fields on your own. These ones are important. Protocol, TTL, version, header length, header checksum, definitely important according to me. The others could be probably, which we might not need at this level, but you can as well do it for the sake of learning. Right, moving to the IPv4. What is an IP address? An IP address identifies a node on a network. IP addresses are used to forward IP packets on the network. So every host, when we're saying host, we're saying every device, every interface on a network everything on a network, it is identified by an IP address. Every device on a network, it is identified by an IP address. When you are sending information from A to B, A needs an IP address, B needs an IP address. That IP address will be used to identify receiver where information yako. And basically that is what the IP is. We have IP version 4, we have IP version 6. Like I already alluded, I think we don't have much here. Let's move a bit quicker. IP address notation. Notation, IP address is basically made of 32 bits. So I think at this point, digital communion number systems will probably need to kick in because the notation yedu takuzoka binary. In IP address, a representation yayo is decimal. When we are looking at it, is SUSU. So this is a typical IP address highlighted here, 192.168.10.1. These are decimal values. So when we're reading those values, it's much easier if we're using decimal. But we all know at this stage that computer systems, they understand binary. So we need to convert this value to binary. Now, you can see my dots are up. Every decimal value is represented by 8 bits. These are the 8 bits reports. Now, what our computer system see is this, and what we see is the decimal value. So I think you definitely need to revisit number systems, conversions from decimal to binary. I think will become very much needed. Also, when we are discussing IPv6, is it here? Let me see. IP structure. Probably it's not there, but we'll discuss it pamberi probably. So IPv4 is 32 bits. IPv6 is 128 bits. This one, instead of decimal, it uses hexadecimal. So on top of understanding decimal binary conversions, you definitely need to understand decimal, hexadecimal, then hexadecimal binary conversions as well. Because typical exam questions would definitely require you to understand that conversion. I won't go through how they're coming up, converting these numbers to binary. I think I'll leave that to you. Simple stuff. IP address structure. An IP address is identified by the network portion, the host portion, and what we call the network mask. In simple terms, let's use this IP address right here. Can I get a screen? Let me see. No, this is Zoom. All right, I can't get a screen somewhere. Just a minute. Let me see. See your slide, show screen, black screen, a white screen. Let's have a white screen. Voila. Right. So an IP address is structure. We're talking about the structure. An IP address in here to the network portion, in here to the host portion, then in here to the network mask or a subnet mask. So if I take an example at this network, you see representation in network in something like this 255.255.0. So what you're looking at is an IP address, this one. And this is the mask. The reason why we have the mask, this value is Joy not like it out to the network portion and the host portion IP address here. So the mask is used to identify the network portion and host portion. That's the importance of mask. Why do we have the network portion and host portion from IP addresses, Edu? I always give an analog. You could see if you are directing someone Harare, probably the network portion is you saying you are going to Harare. But where exactly you need the host portion? Where exactly you are going to Harare, Newlands. So Harare is the network, then Newlands is the host. You realize Newlands is Harare, basically. So the network identifies, the network portion identifies, I think, the larger area, so that unopinda network, unopinda Harare. The host portion then go to a specific place, korofanira kuenda Newlands in this case. Ukangoti Harare, probably it's not uchipama directions. It's not as good because Harare is big. So the network portion, think of Harare, the host portion, think of Newlands. Now, how do you know this is the network portion per number, and this is the host portion? You use the subnet mask. Subnet mask in a simple representation, which uses what we call the prefix length. So the prefix length, instead of putting this number 255, 255, 2550, you can count the number of binary ones that are on this value here. Tikaisa binary, you're going to realize with the first 24 bits, 24 ma 1111. Because 255 is 1, 2, 3, 4, 5, 6, 7, 8. This is 255. Multiply by 3 values, you get 24. So in short, we can say our IP address is 192.168.10.1/24. This becomes very easy now to identify your network and host portion. The network portion, you use this value here, 24. And you say the first 24 bits of my IP address identifies the network portion. So ndikadatarisa the first 24 bits of my IP address is 8, 16, 24, meaning my IP address, network address is 192.168.10.0. This value is Kangoroka Newlands, but ndikaisa 0, this identifies my Harare. So this is my Harare ish. Then ndikazoisa .1, ndakuaddera the host portion, that becomes my Newlands. Ndikaisa .2, that becomes my Highlands. .3, that becomes my Samora. .4, that becomes my Highviews. .5, that becomes my every town within that same network. So basically, this is the structure of the IP address. IP address in a host, in a network portion. How do you identify with the host chip in the IP? Network portion in the IP, you use the subnet mask. Right. Network part identifies the network. I think we've gone through this. Here they used an analog, community A, almost the same thing. So the network part, it identifies community A. The host part, it identifies a street within that community. That is basically what the structure of an IP address has to offer. So if you are looking at this example, so you realize that we are given a network. This is our network here, 10.0.1.0/24. Then the IP addresses within that same network, you can assign addresses for my devices are network E. For example, you can assign 10.0.1.1 is an address. Ndio yakasainwa ishi pa gateway redu. We can assign 10.0.1.2, 10.0.1.3. Tichienda takadaro kusvika kupi. That is what we're going to be learning partial subnetting. I think we'll get to 254 in this case. Right. IP address classification, classful addressing. How many minutes do we have? 7. Right, my IP address is add animal classes. My IP address is add animal classes. We have class A, B, C, D, E. And as you can see, my classes edu, they're identified by my bits. Arikutanga kuti anenge akaita sei. So if you're looking at class A, the way I usually do this, class A, it should be 0/8. Am I correct if I do this? Let me see. 0/8. Class B is 128/16. Class C is 192/24. So basically, we have a range of IP addresses that we use. Class A, this is the range. For easy understanding, I think you can use this value. As we go, you understand exactly what I've written panapa 0/8. It basically means the same thing as this. So the range of IP addresses identifies the class basically. You're going to realize with Pama classes Papa, we have further classification, you in my private IP addresses and my public IP addresses, which will come from my classes. Class A, it a range of addresses that's not private. B and C, we also have a range. But knows what 192.168, it basically means negative class C. When I was networking a little bit more, but not 172.16, turn from class B, but not 10.0.0.1, turn from class A. So range, IP address here determines the class. Why we have my classes is because of the number of hosts that we can have on a given network. So we are going to realize with the class C, for example, the maximum number of IP addresses that we can have, since we are using a /24 network, is 2 to the power of 8. That is 256. So class CE, my networks I can only accommodate 256 devices hosts. Can have a class B, 2 to the power of 16. I'm not sure what's the answer there. Then for this one is 2 to the power of 24. 2 to the power of 24. So class A accommodates a lot of addresses. Class A ndo my networks akakurisisa. Probably this is millions. Let me try to find the value for that. 2 to the power of 24. I think let's put my values all into perspective. 4 minutes. Don't know what I say. 2 to the power of 24. Is this 16 million or 1.6? I think this is 16 million. So this one is approximately 6.7 million addresses within a given network. So that's huge. That's a very huge network. To the power of 16, 65,000. So this one, we have 65K for class B, 65,000. Then for this one, this is 256 for class C. So you can see my classes, they go in order. Name a number of hosts that you can have within that given class. Very important understanding my classes either. IP address types, network address. So we have what we call the network address. I think we've gone through that. We have the broadcast address, then we have the available addresses. I'm going to be using an example to define those three. 3 minutes. Let me see if I can do that in 3 minutes. Right. So provided I have this 192.168.10.0/24. This is my network. This is my network address. Right. Why in network address? Because in the 24 bits here, 24 bits here will correspond to 8, 16, 24, meaning this is my network portion ESA. Then my host portion, though my values are up. This is my network address. When we're discussing the range of addresses within that network address, within that network, my addresses at no one and up, you're going to realize Tiatora 8 bits is rapis. 1, 2, 3, 4, 1, 2, 3, 4. Then totanga kuisa binary yedu ndikatanga na 1 panapa value inonipa 1 ndikaenda naita 0 1 value yonipa 2 then I continue 3 up until I have 1 2 3 4 1 2 3 4 then value inenge ya 250 6. However, handikwanisi kuassigna value ichi ne-all ma-ones ichi. The last value yandinokwanisa kuassigna inenge ina 0 panapo, which is 255. 255 iyi value ichi ndio inonzi broadcast address. So munetwork mako address yekupedzisira -1 ndio inonzi broadcast address. Address yekupedzisira provided you have all ma-ones pa-host portion yako ndio inonzi broadcast address. Is this correct? All ones. 255, 256. It's actually 256 the broadcast here. All ones, 1, 2, 3, 4. 256 is our broadcast here. Then 255, it should be our last address. 1 minute. I think let's start here so that I clarify exactly what I'm doing here. We're trying to explain the network address key, range of IP addresses within the network key, and what is the broadcast IP address. Join me soon after.